Hi, this is Greg Conradi Smith from William and Mary, and this is Lecture 9 of Cellular Biophysics and Modeling, where we discuss voltage clamp recording and the classical biophysics of the squid giant axon. So far in class, most of what we've done can be put into one of three categories. We've discussed the dynamics of neuronal membrane potential, we've discussed measurement of ionic membrane currents, and we've discussed modeling with ordinary differential equations. And in black are all the themes that we've covered sort of so far, the current balance equation, exponential relaxation, current voltage relations for various ionic currents, and the phenomenon of membrane bistability. We've also talked about scalar ordinary differential equations, of which the current balance equation is an example, and phase diagrams. Now, all of the recordings that I've shown you so far are described as current clamp recordings, and in this lecture we're going to introduce a different recording mode that's called voltage clamp recording. We're also going to discuss action potentials or membrane excitability, repetitive spiking or neural oscillations, and eventually we'll be talking about systems of ordinary differential equations and phase plane analysis. So the idea behind voltage clamp is the following. So here I'm showing sort of in an abbreviated form the conservation law for the current balance equation. We have the capacitance times the rate of change of the voltage is equal to an applied current minus the membrane currents of the cell. Now, one of the observations that we can make for the first time is that if the applied current was such that the voltage was equal to a particular command potential, and we were in a situation where the rate of change of the voltage was nearly zero, then the applied current would actually have to be equal to the membrane current. What this means is that if we had electrical equipment that could inject current into the cell in order to maintain a voltage pulse as a function of time, then except for these transients where the jumps in the command potential occur, the rate of change of voltage is going to be zero. And that means that the applied current required to maintain that command voltage is actually a measurement of the membrane currents that are flowing in response to those voltage pulses. This might sound complicated and backwards, but we'll go over it again and again throughout this talk and the next. So, in summary, the applied current that's required to maintain the command voltage essentially measures the changing membrane currents evoked by the command voltage. That's the basic idea of voltage clamp recording. So now we have these two different configurations of electrical measurements of living cells, and we're going to need to keep track of which configuration that we're in. So anytime you see a figure, you're going to need to ask yourself whether we're looking at a current clamp experiment or a voltage clamp experiment. So let's start with current clamp, although I haven't used this phrase yet. This is essentially what we've been doing up to this point in class. So in current clamp recording, we are injecting a prescribed amount of applied current into the cell membrane, and we are watching or recording the cell voltage that change in response to that step in the applied current. And we've seen this several times before. If you have a current of zero, you'll be at the resting membrane potential, and then when this current steps up, that will cause positive charge to enter the cell, and it will lead to depolarization. And then when the pulse is over and return to zero applied current, then that voltage will hyperpolarize again and go back to rest. So this is the ordinary differential equation that we've been considering for to represent this case. And we're essentially thinking of the applied current here as being under experimental control, so that whatever shape of pulse or the timing of multiple pulses wanted to be applied, with the experimentalist could sort of dial that in and do that. And then what's being recorded is the response of the membrane potential as a function of time. So the applied current is the drive. It's what's changing in this way as a function of time. Membrane currents are then also flowing as the voltage changes, and this rate of change of the voltage is essentially determining whether whether you're increasing or decreasing as a function of time, based on the balance between the applied current and the membrane currents that are flowing. Now, in voltage clamp recording, it's really different. It's kind of backwards compared to current clamp. And what's meant by this word clamp is that in this case, it's actually this command voltage that's under experimental control. So the experimentalist will dial in a command voltage. For example, this pulse that's maybe 200 milliseconds in duration long and maybe 40 millivolts high. And then the equipment is going to essentially inject applied current in order to make sure that this is the voltage that the cell membrane follows. Now, if you think about that, that means that the current that has to be injected to maintain this command voltage as a function of time has to balance all of the membrane currents. There's two components. There's the capacitive part and the resistive or ionic part of those membrane currents. And so, except for a brief period of time when the command voltage is rapidly increasing or decreasing, the rate of change of the voltage is actually essentially zero. So in this phase, the rate of change of the voltage is zero. That's also true here. That's also true at the beginning of the experiment. When the rate of change of the voltage is near zero, then the applied current that's being injected is actually measuring the ionic currents that are flowing. And those ionic currents might be larger or smaller depending upon the command voltage. So in this voltage clamp recording setup, the command voltage is the input, and the recorded membrane currents, the recording of the membrane currents that were flowing in response to that step in the command voltage, are what is sort of the measurement that's taking place. These little vertical lines here are called capacitive transients, and you can read about them in the appropriate chapter of the Cellular Biophysics and Modeling textbook. So the point of voltage clamp recording is that it shows how ionic currents activate over time. So in this example, we're showing a command voltage jumping from minus 70 millivolts, which is the resting membrane potential of a cell, to minus 10 millivolts. So it's been deep, the command voltage has increased by 60 millivolts. And that's held for maybe 400 milliseconds or so. And what you're seeing up top is the applied current that was required to make this be the cell membrane potential. Now there's two pieces. There's the capacitive part and the ionic part, or the resistive part. And we're primarily interested in the membrane currents, the ionic currents that flow in response to this change in the command voltage. Here, what we see is when we depolarize the membrane, an outward current began to flow, an outward membrane current, right? Positive membrane currents are outward. This activation, we can as a function of time, can actually be seen in this type of recording. And then when the voltage is returned to rest, these channels deactivate, the current deactivates, and the ionic membrane current goes back to 0, which is what it was when we were at rest. So the example that I just showed you was essentially a measurement of a particular type of ionic current called the delayed rectifier potassium current. So here's an experimental record showing that sort of voltage clamp recording that we've been talking about. Here, the command voltage is being described as E sub m, the voltage that the membrane is going to be held at. And the currents that are flowing in response to that are I sub m. Now, the thing to note is that in this, there's a couple things to say. One is that when we depolarize, we're turning on an outward current. And the other is that it takes some time for that outward current to actually fully develop. So initially, right, there isn't as much outward current flowing as there is at later times. And if you looked at the exponential time constant here, it's taking a couple of seconds for this outward membrane current to be evoked by the step change in the command voltage. Now, I refer to these as plateau currents because it's looking like they were exponentially relaxing to some fixed value that would correspond to whatever voltage was being stepped to here. The type of current that we're referring to in this case is a potassium current. It goes by the name of IKV, or a voltage gated potassium current. Sometimes it's called IKDR for the delayed rectifier potassium current. These are essentially interchangeable terms. And if you were going to summarize, remember this is sort of a sequence of 8 to 10 different steps, right, in the evoked membrane currents that occur. And if we wanted to summarize all of this, well, what we could do is we could plot the ultimate membrane current that's attained as a function of the step voltage, the command voltage that we have during this depolarizing pulse. So that's what's happening on the next slide, right? Here's let's look over here on the left first. These are steps in the command voltage evoking an outward current. And ultimately there's a plateau outward current, meaning the current that's flowing is given by whatever the step potential was. It's fully activated. And we can plot then for every step voltage, we can plot the plateau current that flowed, and that would, in this case, give a outward rectifying shaped plateau current sketch here in a graph of the membrane current that's flowing as a function of the voltage step. And if you think about what's happening a little bit earlier, this current wouldn't have developed fully, and so it would be less outward. There'd be less outward current flowing if you sort of do the similar plot at a shorter period of time. Now, for a long time since Hodgkin and Huxley, ionic current activation has been modeled using an ordinary differential equation for a so-called gating variable. And the dynamics of that gating variable will be an exponential relaxation written in the form that you see here in the middle of the screen. So what I'm saying is that the potassium membrane current, this is written as the delayed rectifier potassium current, is a conductance times a driving force. This is the membrane voltage less the Nernst equilibrium potential for potassium. And what we're going to do is put a variable that can take values between 0 and 1 and raise it to some power. And it's going to sit here between the conductance and the driving force. And it's essentially, whatever this number is, it's representing the fraction of these potassium channels that are open at a given time. Now, the way that this was set up by Hodgkin and Huxley is they would say that the dynamics of this gating variable would exponentially relax to a steady state that they described as m infinity of voltage. And that steady state is plotted over here on the left. So this is the activation function for the potassium channels. And this is a time constant that also depends on voltage. So we haven't run into this phenomenon before, having our sort of essentially linear kinetics, but the exponential time constant depending on the one of the dependent variables. This is sort of new, but essentially what it's saying is that, if the voltage is a given value, ultimately this is the fraction of the channels that will be open, either all of them when you're really depolarized or none of them when you're hyperpolarized. And the time that it takes for M to evolve towards this steady state value will depend on the voltage. You can see that when the voltage is made more extreme, this time constant gets smaller, meaning that you will relax to the steady state value more quickly when the voltage step has been extreme. So now calcium currents also can activate gradually. So this is an example of depolarizing steps in the command voltage that activate an inward current, right? So this is an inward membrane current because it's a downward deflection. Negative membrane currents are inward. And what you can see here is that depending on the step voltage, a different amount of inward current flows. Once again, it took a couple of milliseconds for this current to actually develop. It took a couple seconds for the ion channels responsible for the calcium current to open. And this current is referred to as ICA or ICAV, meaning voltage-gated calcium current. And here is a plot of the plateau current in this experiment. Now we're showing more results here, more different. There's a larger number of step voltages shown here than just the 3 that are in this plot, but the correspondence is easy to see with the red dots in both cases. And this current voltage relationship, which has been measured using the voltage clamp technique, looks a lot like what we've been calling the regenerative membrane current, kind of the qualitative form of what we called a regenerative membrane current. Both voltage-gated sodium currents and voltage-gated calcium currents kind of look like this. But what's different is I'm not just showing you the current voltage relationship, I'm showing you how the current voltage relationship was measured experimentally. And that's the beauty of voltage clamp. That's what voltage clamp is actually doing. Voltage clamp technique is where these current voltage relationships have all come from. So far I've just discussed what I would say are persistent currents. And what I mean by that is that after this voltage pulse, during the voltage pulse, a certain amount of current is recruited and it sort of levels out to some persistent or plateau membrane current that would presumably remain there in forever, except that the command voltage drops back down and then the current stops flowing. Okay. So for the case of persistent currents, there's 4 broad classes that we would refer to as either depolarization activated outward currents. So this is the depolarizing command voltage step. and then this is the outward membrane current that's flowing. But you could also have depolarization activated inward currents. So this was like the delayed rectifier was this type. The potassium, the IKV current, the voltage gated potassium current was of this type, and the voltage gated calcium current was of this type. Those are the two that we've sort of discussed so far. But you also can have currents that are activated when you hyperpolarize the membrane. You know, we've hinted at that in previous lectures, but here is what that would look like in a voltage clamp recording. So when the command potential is hyperpolarized by 30 millivolts or so, in this schematic you can see capacitive transients, but then if you ignore those, you see this outward current that has been activated in response to the hyperpolarizing voltage. And here's a inward membrane current activated by hyperpolarization. So you have inward and outward currents that are activated either by depolarization or hyperpolarization of the cell membrane. So that gives you sort of 4 fundamental cases for currents that are persistent. This is the picture of inward current that's activated by hyperpolarization, right? So the membrane is, you have a range of voltage steps here, and you can see in the current voltage relationship that's been measured that the plateau current that's flowing is never outward, it's only inward. But the correspondence between these plateau currents and these voltage steps is sort of, might be backwards from what you're expecting. In this plot, you can actually see that the more hyperpolarizing the voltage step, the more inward currents flowing. Now here's another wrinkle. Ionic membrane currents are often transient as opposed to being persistent. So what we mean by this is that in a voltage clamp experiment, the recorded membrane current will sometimes go through 2 phases, so we'll have a biphasic response. The upward phase when channels are opening is called activation, and then after that there will be a phase of inactivation, where the channels are closing again. So the difference, the reason why this current would be referred to as transient is that, you know, current is recruited by the depolarizing command potential, but after a little while it starts to go away on its own, even though the command potential is depolarized. Here's an experimental measurement of sodium currents, and it's very similar in the case of calcium. There's a depolarizing command potential here, starting from rest and then going up 40 millivolts or so. And then this is the evoked membrane current as a function of time. The control case here is this one, right? The current goes down and then up again. This is a recruitment of a negative membrane current or an inward membrane current. And then that's the activation phase, followed by an inactivation phase, so that ultimately the amount of inward current that's flowing is quite a bit less than the peak amount of inward current that was flowing. Now, there's actually multiple membrane currents that are that exist in the cell membrane, and the voltage-gated sodium current is only one of those. And experimentally, you can sort of dissect what currents are actually present, even in cases where there are multiple currents, by changing various quantities. You can, pharmacologically block currents that you already feel you understand. You can also change ionic concentrations outside the cell, right? That's under experimental control. So here in this old experiment, they reduced the extracellular sodium concentration, and in that case, inward, this the amount of inward current here that flowed was significantly less than it was when there was 100 millimolar sodium. So the interpretation here was that this current, this inward current that was activated by depolarization, was mediated not by sodium but by calcium. And the part of that the inward current that was mediated by sodium is reflected in this difference here. Okay, so transient currents also come in multiple varieties. So you can have a depolarization activated outward current that's transient, right? There's two phases here. You could have a depolarization activated inward current, which will look like this, a hyperpolarization activated outward current, and a hyperpolarization activated inward current. So that's sort of our taxonomy of all the different things that we might see. And then there's going to be this principle that sometimes there'll be an experimental manipulation that is trying to remove one of multiple currents that are thought to be flowing in response to that changing command potential. So that is it for this first part of our lecture on voltage-gated ion channels and their time-dependent dynamics of activation and inactivation. This is Greg Conradi Smith from William & Mary. Thanks for listening.